aluminium is indeed reactive. The thermite reaction, where aluminium powder is mixed with iron oxide and ignited. The violent reaction liberating molten iron shows that aluminium is higher than iron in the reactivity table. Make a very concentrated solution of copper chloride, just enough water to dissolve the crystals to make a green soup. Then add aluminium powder. In the violent reaction that follows, copper is displaced and forms a brown residue, and clouds of aluminium chloride vapor and steam come off. But whether it is aluminium cooking utensils, cooking foil, drink cans, window frames, or aeroplanes, you see the shiny metal left out in all weather, which does not seem to corrode. To understand why aluminium is used so widely, let's think of its useful properties. Pause and think why aluminium is used so much. It is abundant. Aluminium is the commonest metallic element in the Earth's crust, though most is locked up in clay as aluminium silicate. Even so, there is no shortage of the metal ore bauxite, but being so reactive, it uses huge amounts of electrical energy to extract. It is for this reason that collecting and recycling aluminium containers is particularly important, costing only a fraction of its extraction costs. It is a metal. It is strong but can bend without cracking. When alloyed with small amounts of other metals, such as copper, it is very strong, meaning it can be shaped for use in buildings, such as window frames. It has a very low density, so especially useful for making aeroplanes, trains, bikes, and the superstructures of ships. It conducts electricity. If you compare aluminium and copper wires of equal thickness, aluminium is not as good an electrical conductor as copper, but if you compare their weights, aluminium is better. So it is used in all high-voltage overhead electrical transmission cables. It doesn't corrode, meaning it can be used without being painted. The secret of its lack of apparent reactivity is a hard, thin layer of oxide that forms all over exposed surfaces. This layer is so tight that water and air cannot get under it. If it gets scratched, a new thin oxide layer immediately forms, stopping further corrosion. Compare this with iron, where the rust layer does not fit tightly, and water and air can readily get to the fresh metal. You may have seen shiny, brightly coloured, almost metal-like parts of bicycles, kettles, utensils, and so on. These are made of what is called anodized aluminium. The anodizing process builds up the protective oxide layer by making the aluminium the anode of an electrolytic cell containing an acid. At the anode, hydroxide ions arrive and give up their electrons, forming oxygen atoms, which then react with aluminium to build up the oxide layer. The new layer is very hard, inert, and can absorb dyes to colour the film, giving the bright shiny colours like this. The film is chemically bonded to the aluminium, forming an integral part of the structure, in contrast to, say, a paint or electroplating. However, the film is electrically insulating, so the aluminium that is protected and coloured this way cannot be used in electrical circuits.